Anyway, so I'm Pierre. I'm the CEO and co-founder of C12, and I'm very happy to be here. So at C12, our profound conviction is that we need to build quantum computers differently. We need to build them different by design, from the first qubit you built up to the million. And today, first I will share our vision and what are we building and why are we building carbon nanotube qubits. And then I'm very excited also to share a breakthrough results that we achieved this year. And last, I will focus on what are the next steps and when we will be able to offer this product to our customer. So we don't have quantum computer yet. We don't have them yet because they are bugged with error. We don't have them yet also because the error rate is increasing when we scale the number of qubits. And we don't have them yet because what we think is that we are optimizing some quantum approaches without having the right material. Because the fundamental challenge of this revolutionary machine is that quantum material interact very easily with their environment. And at the end, it's a very simple fact. All these errors, they come from defects in the qubit material. So if you have a perfect environment, no perturbation of your qubits, then you have no errors. And I think that now it's a fact that makes some consensus within the scientific community and the quantum industry. I pick one quote from a great scientist, Admire, and what he is saying is that if we really want to build a large-scale fault-tolerant quantum computer, we need a breakthrough in terms of material. Or said differently by John Preskill, we need much better qubits. And so at C12, we leapfrog this material gap by introducing the carbon nanotube. The carbon nanotube is the most minimal electrical wire you can imagine. And it has some incredible properties as a material. And at C12, we know how to turn them into a quantum transistor. And carbon nanotube is indeed resolve what we can call the quantum paradox. So we can make qubits extremely well isolated, but at the same time, we can address them well. And so our vision is that all quantum computer will be based on carbon nanotube qubit on one day. And we like analogy. And if we take, for example, the early days of the semiconductor industry, the silicon was not at all the obvious material for building classical transistor. And there were a lot of investment going to other material like germanium, like a 3,5 material. But was missing, people knew that silicon had the right fundamental property, but what was missing was the manufacturing process. And when the manufacturing process was actually solved, all the other material become obsolete, and the silicon enabled the emergence of all the classical compute that we know. And this is really the vision that we have for carbon nanotube. So if we zoom in, how does it look? How does a carbon nanotube qubit look like? So it's a spin qubit technology, and we encode our qubits in the spin of a single electron that is trapped into a suspended carbon nanotube. And why this is an incredible material? Because it protects this spin qubit from any sources of errors. And actually, you have only like 3 sources of error. Either they come from magnetic perturbation, or they can come from electrostatic perturbation, so some charge that are trapped close to your qubit material, or they can come from mechanical perturbation, like a phononic mode. So we have now the numbers to show that indeed we have the best material to make qubits. So if we start with the magnetic perturbation, they are coming from nuclear spin that are close to your electronic spin. And on this, actually, this is why we are called C12. It's because we are using the isotope 12 of the carbon, which is without nuclear spin. And we can have actually less than 1 nuclear spin per qubit, per dot. So we are in a nuclear spin-free environment for our qubits. Second thing is how this suspended architecture protects extremely well our qubit from charge noise. And we know that charge noise is the worst enemy for high fidelity in speed qubit technology. And so we achieve, it was measured with our research partner, Mark Bittler at UCL in London, the lowest sensibility to charge noise, whatever is the material. And the last is the protection against mechanical vibration. And here, it's kind of a trick, is because the carbon nanotube is a 1D material, so he has some confined vibration mode, and you can engineer your qubits to be well uncoupled from any vibration. And so that's why we have like a relaxation time much higher than what you can have in other solid-state platforms. So these are the data that we have on carbon nanotube, showing that we have the best material to make the most performing qubits. So this is really why we are doing this. We have chosen the best material to make qubits, and we have also the platform that is on silicon. So we combine really minimal error with high scalability. So how do we to position ourselves with other approaches? And I think that now we know that we need many qubits and also high quality qubits if we want quantum computer to have a massive impact and to run really useful quantum algorithm. So if you take atoms and ions, they have extremely high quality qubits, but they have kind of fundamental limits to have more than 1,000 or a few thousand qubits in their system. On the other side, superconducting qubits, they have a great scalability potential being on chip. However, they have reached the kind of limits in terms of current time, like close to a few hundreds of microseconds. So at C12, we have a roadmap to deliver 1 millisecond of current time on the physical qubits on this silicon platform where this is highly manufacturable and scalable. And on top of qubit quality and scalability, I think that what is absolutely great about this technology is that there is no roadblock on all the necessary ingredients to have a full-scale fault-tolerant quantum computer. So if you take, for example, speed, we perform gates through microwave, so we have the same speed as we can have with superconducting qubits. Our qubit footprint is extremely small, so 10,000 times smaller than a superconducting qubit. We can also offer higher connectivity, and I will go back to this just later on. So we have in our architecture a quantum communication bus that links the carbon nanotube between each other, and this is how we can have like higher connectivity. And actually, I was pleased to see that IBM had the C coupler in their roadmap to enable non-local qubit-qubit interaction. And I think that it's a great news that the industry is going to that direction. At C12, we started from the start to have this quantum bus within our architecture. And the last thing is that it's a semiconductor qubit, so it's consumed 50% less than a superconducting qubit. So now is time to share the big results that we achieved this year. Incredible work of all the C12 R&D team and our research collaborator at École Normale Supérieure. So there is probably a few big milestones that we will have to achieve to, at the end, deliver a full-scale quantum computer. And this is one of them. So this year, we demonstrate the first qubit operation on our quantum computer. So the first time manipulation of our qubit. Before, we were only addressing our qubits in the frequency domain. And for the first time, we were able to perform an operation. And we were extremely surprised in the positive sense about the performance that we were able to achieve with these qubits, especially in terms of occurrence time. So as you may know, there are two kinds of errors. You have bit flip error, so when the qubit goes from state 1 to state 0, and you have phase flip error. And these two errors, they are linked to a specific occurrence time. So for the bit flip is T1, and for the phase flip is T2 star. And both of this time were above the microsecond. So the first thing is that before the last coherence time that was measured for carbon nanotube qubit was rather on the a dozen of nanoseconds. So it was a huge improvement of what has been measured. And the second thing is that T1 and T2 star are on the same order of magnitude. And this is very different from what you expect, what you usually have in spin qubit or superconducting qubit. And this is really the sign that we, with this technology, with this material, you are able to protect the qubit from all kind of errors. How we perform this first qubit manipulation is through the microwave resonator. So we did not simplify the problem. We really did how we want to do it in the long term, meaning using this very important component of our architecture, which is the communication bus. So it is the green line that you can see on the slide and that link the qubits. And what we think is that this kind of architecture with the quantum communication bus is really what will enable us to scale solid-state architecture. And so it's another also record that I'm pleased to share. So there are several research groups working on coupling spin qubits to microwave resonator. And with this microsecond long coherence time, we actually have the world record, the longest coherence time measure for a spin coupled to a microwave resonator. And last point maybe about this microwave resonator, this quantum communication bus, or this C-coupler, however you want to call it. I think it has many advantages. The first one is that indeed it enables low crosstalk between your qubits because you are not restricted to nearest neighbor interaction. The second thing is that it also offers a way to have higher connectivity. And last, it enables non-local qubit-qubit interaction. And we know now that to have a way to have non-local qubit-qubit interaction opens a way to have much more efficient quantum error correction code. Now maybe a few words about C12 and also a few words about our next steps and when our technology will be indeed ready to use. So we are a Paris-based quantum startups founded in 2020. We are now 36 people. We have a portfolio of 6 patents, both on the manufacturing and the design of our chip. And we focus mostly on quantum chemistry for our first application. And this year also, with 18 months of work, we officially commissioned our pilot production lab. So it's a you would not expect to find such a quantum fab in the center of Paris. So it's a bit hidden, very close to official buildings. But we have like our own clean room, and we have also all the labs that we need to fabricate our chip in-house. And we also have the cryostat that we need to operate and measure our chip. And you have a few pictures of the space here. So at C12, we are really a hardware-focused company. What does it mean to focus on the hardware is supposed to build those groundbreaking quantum chips, but it's also to deliver the low-level control software. Everything that is above this control software is something where we develop with partners. So our chip is compatible with any SDK that exists out there, at least the most widely used, like Qiskit or Tket. And we partner also with a software company when we want to develop an application. At C12, we are very convinced that it's important to have two roadmaps progressing in parallel. The scientific and tech roadmap, focusing on some very important tech milestone, and the result I share with you today was a significant milestone on our tech roadmap, but also to have like a product roadmap able to engage early on with a customer. So this year we released Callisto, which is our 13-qubit emulator. And we are already working with a customer in the chemical industry to develop some interesting use cases. And in 2025, we will have our first hardware product, first the 5-qubit chip. And so this will be a coprocessor technology. So it will meant to run hybrid quantum classical algorithm. But the end goal is, and we know even more that after Preskill's talk yesterday, it's to deliver an error-corrected full-scale quantum computer, because this is really where we will have like the most massive impact for industries and for our society. One thing that we are we think that is the way we think about like delivering this full-scale quantum computer is that we need really two ingredients. We need to demonstrate error correction, and that's of course very important. But we also need to show that we are on the right direction to industrialize. And this is why there's two, we think, very important necessary steps to then be able to deliver a full-scale quantum error-corrected quantum computer. And when we say industrialization is both in the manufacturing process, where we also invest a lot, and in like a product scaling. So this is our technology. This was our big result I was very happy to share with you today. And this is our journey at C12. Thank you very much.
Yeah, let me grab a mic for you for questions.
Thank you. What percentage of impurity can you tolerate in the nanotube, and how do you get rid of it? Isotopes and things like that.
Yeah, thank you. It's a very important question, how you cope with like qubit-to-qubit variability. And it's an even more relevant question for carbon nanotube, which is not to show some variability. So what we have actually is our manufacturing process enable us that the integration of the carbon nanotube is really done at the last step of our fabrication. And so after we fabricate our carbon nanotube, we have some quite advanced characterization technique. It's a mix actually of spectroscopy and electrical characterization. And thanks to this technique, we are able to select the carbon nanotube that will do the most performing qubit. So on this, we are very selective. This is where we have the lowest yields. So the challenge is that you want to do this pre-selection with a very short time budget, because if you spend too much time to select the carbon nanotube, then this is where you can have a problem when scaling. So this is what we are working on.
One more question.
What kind of nanotube do you use? Metallic or semiconductor?
So this we are using semiconductor carbon nanotube, narrow band gap. These are the one we love.
Single wall carbon nanotube.
We are using single wall carbon nanotube. Well, thank you so much.